Good evening and welcome to the final lecture of the fall 2014 Baumer Lecture Series. My name is Andrew Cruz. I'm an assistant professor in the architecture section of the Knowlton School. Forrest Meggers' lecture tonight is going to be an unusual treat. Unusual because Forrest is not an architect, a landscape architect, or a city or regional planner, but an engineer, and a mechanical engineer, to be more specific. In theory, this should not be unusual since the Knowlton School is part of OSU's College of Engineering, and it should be natural to have an engineer taught within the College of Engineering. But in practice, we in Knowlton Hall often wear the same blinders that many other professions wear. We like to hear from our own about our own. For architects, that means hearing from other architects about buildings. This is where the treat part comes in. For tonight's presentation, Forrest is going to talk to us about buildings. Although his list of research interests is full of terms like Exergy design and low temperature hybrid solar, his PhD is from the architecture department. Tonight he will talk about integrating building performance into the design process. Technology invigorating architecture is how it puts it in the title of the talk. Invigorating is a good verb. Wouldn't you like to be invigorated in this, the 13th week of the semester? I know that I would. Invigorating architecture through technology is not a commonly held goal when it comes to issues of energy and comfort, two of a mechanical engineer's main concerns. Instead, architects and mechanical engineers typically follow a typical division of labor. The architect makes the shape and the spaces. The mechanical engineer figures out how to make most people comfortable in them. Concerns for efficiency often still mean still keeping everybody comfortable, but just using less energy. And hopefully making the ductwork smaller, or maybe making it disappear through the magic of radiant energy. Invigorating architecture through technology in the way I think Forrest will talk about it doesn't accept business as usual. Instead, ideas of comfort and energy provide new dynamic conceptual approaches to design and new opportunities for collaborations among the professions of architecture and engineering. Such an approach can break through tensions that typically exist between creative expression and public obligation, inherent in any combination of architecture and energy, bringing both new building forms and new forms of social engagement. 25 years ago, the Spanish historian and critic Luis Hernandez Galeano wrote in Fire and Memory, "Energy brings architecture into the world of process and life, but it also bestows architecture with consumption, fugacity, and irreversible time. Architecture brings together fire and light, chaos and organization." When architects, historians, and theorists have sought to define what is essential to architecture, what makes it different from the other arts, they have traditionally seized upon issues of structure, function, form, and space. Energy and comfort have not been considered as essential qualities of architecture. I think in what you will see tonight, Forrest will try to expand our understanding of what is essential to architecture, and in doing so, provide new opportunities for architects and engineers alike. After Forrest's talk, I would like to invite you to an opening in the Baumer Gallery for a show I've put together called In the Air, Seeing Architectural Climates. The show looks at architectural representation of climate and how architects have engaged with issues of energy, comfort, and environment as part of the design process. Finally, for the pro forma part of an introduction, Forrest Meggers is an assistant professor at Princeton University with the joint appointment between the School of Architecture and the Adlinger Center for Energy and the Environment. Originally trained as a mechanical engineer in his native Iowa, Forrest earned his PhD at the ETH in Zurich in the Department of Architecture. He then worked as a senior researcher in the Singapore ETH Center for Future Cities Laboratory in Singapore, and then as an assistant professor in the Department of Architecture at the National University of Singapore. I first met Forrest at a conference he organized last spring at Princeton entitled Forward and Backwards on the Legacy of the School's Architectural Laboratory that included the work of John Magatu, Victor and Alvaro Olge, David Billington, and now Forrest and his colleagues. This is an impressive legacy, and one which we look forward to hearing and seeing more about in Forrest's presentation tonight.
Thank you very much, and that was by far the best introduction I've ever gotten. I'm very excited to be here. Even though I am from Iowa, it's a little bit hard for me. I'm from Iowa City, another big school, but it's worth it, and I'm very excited to be able to meet some of your faculty here. It's very lucky to have people like Andrew putting on these wonderful events, like the exhibition, which I very much look forward to seeing and discussing with you all further later. But as was alluded to, I have a very interesting position standing across the disciplines of engineering and architecture.
Did you turn the one on your pocket
on? Here we go. Louder. So, as I was saying, how much louder? I had to bridge these two very different areas, and in doing so, come up with exciting titles like technology and invigorating architecture in order to try and leverage the interest that comes from very different places in the minds of engineers and architects. But unfortunately, most often when I just present the ideas of technology, things that I've worked on very hard over the past 10 years, what I find is just presenting the technological aspect of things in architecture schools. The result is usually one of technology infuriating architects because I'm telling them, you have to do this, your walls have to perform, you have to have a green building, you have to have a high performance building. And this isn't necessarily what architects want to hear, right? You want to be able to design things, you want to have some freedom, you want to be able to explore. And so often the whole idea of technology being prescriptive is something that is a challenge because as an engineer you're trained how to prescribe technologies, right? And the problem in architecture is often as technology gets prescribed, you get results like this. As an engineer, I might say, this building is fantastic. This is a passive house. That means it needs no heating at all. It will just heat based on the presence of humans and machines inside. The internal loads will heat the whole building. And any electricity that we need will be provided emission-free from our beautiful solar panels, right? But what is this? These are just prescribed add-ons, right? So the problem is that it's hard to appreciate this as a design output for a building. So my question for you is this better? How many people know this building here? Somebody knows? I'm proving you're better than the Ivy League schools. Someone knows this building, right? Okay. The people at Berkeley knew the building, but they're all in California. So this building is a net zero energy, net zero water. How many people know what the living building challenge is? This is like this is beyond LEED Platinum, right? This is the new greenest of the green. And what this building does, right, is amazing what it can do. And it produces all its own energy. And does anybody want to guess what this building might be? Doing this all solar panels? Solar energy. It's in Seattle, right? Seattle. But unfortunately, when we present this to people in my school, School of Architecture, they don't appreciate the aesthetic, right? And one of the main reasons when I have a discussion about this building, I say, amazing, it's in Seattle, it has zero energy, it has enough solar panels to do energy. The response to that exact statement is, this building has a hat. And it has a hat, and this building has a hat. Does this building have a hat because the architect designed it, because he had this great fondness for hats? No, and there was no other design impetus for putting the hat on the building. The building has a hat because it's prescribed by achieving the zero energy part. So the form of the building is constrained by the standard that you're trying to meet, right? And so the challenge really is how do you play with technology in a way that tries to minimize as much as possible the constraints that are placed on the design process. And so that's the game that I've been playing, both in terms of technology and as well as physical phenomena and theory, and how we can utilize different ideas to better enable architects to engage in in technology in a way that's interesting and invigorating, I guess, right? That's cool. But there's another side of the coin, right? And that is what about architecture is infuriating engineers. I have a history where I was first trained, as I mentioned, as an engineer, and for me, the thing that really pissed me off the most about buildings was when they look like this. And that's because I looked at this and said, man, there's a lot of heat being lost to these glass facades. And not only that, but if you look at the wall, right, how much of that glass do you really need? I mean, for me, I'm just thinking you only need glass to look through, right? And there's like huge walls in front of the glass, and it's all, you know. So what was the point of it? So as an engineer back in the early days, and when I first traveled to New York, I of course was thinking about our fundamentals of physics in buildings, how the heat loss of the building is related to several things, and I have the architecture version of the equation for you. Heat is equal to the insulation times the area times the change in temperature across that area, right? And so that's what's going through my brain. I look at this wall and I say, oh my God, it has a huge area and terrible insulation, so we're going to have a huge amount of heat loss and a huge amount of demand to run this building. And that makes me feel bad, right? Because I also studied environmental engineering, and in that process learned a lot about carbon emissions. So one of the things then that was driving me in the direction of working on buildings was that when I studied buildings in general, this is what the IPCC says about the amount of emissions directly from buildings. When we look at these other sectors, like energy supply specifically, 3/4 of all the electricity in the U.S. is generated for buildings. So 3/4 of this plus a huge amount of industry is actually operated buildings. Waste and wastewater is generated by buildings. All these components have huge sectors, so when we re-aggregate them, we actually find that buildings are one of the largest single drivers of CO2 emissions and global warming. And for me, that was a big reason why I wanted to look at how to make buildings have less glass, right, initially. And the problem, though, is that this problem, because it's made up of all these different components, that many aspects and many different fuels and many components, it's not the same necessarily as concrete emissions, right? They just come from the manufacture of concrete. The building is made up of concrete. Some of those emissions are generated by the construction of buildings. Then we have the operation, which is the largest point. And so that's what I focused on mainly, was this idea of the electricity and heat that we have to leverage in order to operate our buildings in huge portions. And so the driving force as an engineer then, and as an environmental engineer, is that because buildings are one of the most significant sources of emission, 2/3 of global electricity consumption and 1/3 of all waste production, it was very important to me, and now more recently that 2 degrees of warming is pretty much in the bag already, based on the most recent IPCC International Governmental Panel on Climate Change. The 5th report that just came out is a little bit more ominous, and so I think there's a huge reason to start looking at this. But as I was just talking with Jeff Pippis here about, it's not all necessarily about limiting the consumption of the resources. There's clearly 2 factors going on here. We have to limit the emissions that are going on, but also adapt to the changes that will be happening due to those emissions. So buildings are in a very unique place when we talk about what does this mean for design, technology, and how we react to the current situation. So although these emissions need to be mitigated, the actual climate change and temperature and weather has influences on how we design and operate buildings. And all these different components, from the emissions themselves to the life cycle to sea rise and temperature rise, have direct impacts on the way we think about buildings. And this is one of the reasons that today not only does sustainability come up often as a central issue in buildings, but now more and more so resiliency, right? So these 2 things really need to be considered in terms of how you frame the initial driver for why would you want to have this building with a giant hat on it in the first place. And for my focus in terms of the engineering side, where my background is, it's more in the mitigation component, the operation of buildings. So initially, the idea is how do we actually address this? And one important thing we're talking about, for example, the first building with lots of insulation and the second one with renewable energy, is that there's really two places we can work. We can move down the performance line, right, by increasing the efficiency of buildings, often labeled the low-hanging fruit. So this would be things like increasing insulation, improving efficiencies, and then, of course, moving down the amount of emissions that is in the energy we're consuming. So this represents the amount, the amount of energy we're using, and this is the amount of CO2 that's in the energy. So if we put if we put PV panels on, then we reduce the amount of CO2 in our electricity. So this is a framework we created for the operation of buildings and trying to define which path, when we combine efficiency and renewables, how do we strive to reduce then the overall emissions that buildings are having, the overall impact on greenhouse gas emissions and global warming. In order to do this, though, this requires a different view of performance, and that's where I sort of stepped in and started to change the way I thought. Initially, standing back in Iowa, really not so fun today, I was thinking more in terms of why I hated that glass wall, right? And what's happened now is I've moved and looked more rather at this glass wall, but rather at the fact that these two things are in different silos. And I think that's the biggest problem we face, and Andrew alluded to already in his excellent introduction, that engineers and architects have different interfaces. And right now, there's a lot of limitations in how we silo our disciplines. And so, metaphorically, I'm trying to bring those together. And in doing so, this is sort of the background that brought me to this place. Instead of just being an engineer looking at glass facades that I think are efficient, more thinking of how holistically we can approach architecture as something that can be engaged by multiple disciplines simultaneously. And at ETH Zurich, there was the opportunity in being in the building systems group, directly integrated in studio and design culture at the architecture school, and then followed by my work in Singapore, where we were working on physical projects, studying phenomena in buildings that can be used as direct drivers into the design process, and then finally now landing in this joint appointment between the engineering school as part of the Engineering Center for the Engineering Environment and in the School of Architecture. So, what premise then changed about my view on glass? If we start to look at glass differently, it might be to think about that we overlooked a piece when I presented that first diagram, right? And that is that there's another factor in that equation, and that was the temperature. And the temperature, right, we think, well, yeah, that's the environment. We don't control the environment. The environment has a fixed temperature, but in fact, and the building has a fixed temperature because we need to be comfortable. But in reality, rendering this as just a facade is really the issue with our perspective. There's a lot of things going on behind this facade that have to do with how energy gets delivered and moved around the buildings, and the place that we perceive energy being used in the building, the physical comfort that is delivered to us inside compared to especially outside today. That is something that is highly influenced by the type of tools that we utilize to define the performance within a building, right? So right now, we mainly focus on this equation that tells us how much heat loss is happening in the building. That's very important. An engineer would need that to put the right size chiller, the right size boiler, heat exchanger in the building so it stays warm. But in terms of how that heat moves from that system into the building, that's something that's often overlooked and in fact doesn't just play a role in the engineering process, but also in many of the design aspects. In this room, you can see plenty of things, from diffusers, heaters, return lights, to how the lighting is laid out. All these different functions are influenced by how energy is moved around in the building. So the new paradigm, right, that I would propose is this one, Exergy. So what exactly is I'm spelling? It's a way to create a better evaluation of the value of energy. And the analogy I like to use is this one with money. So it's all about the Benjamins are here, the $50 bill or the $50 Singapore bill. And if I were to bring my Singapore money here and try to buy myself a coffee, obviously it's not going to work. Everybody understands clearly there's a different value in these different currencies. Well, when we operate in the realm of energy, when we talk about the heat we deliver to a building from a boiler versus the electricity that would come into the building, these would both be represented in amounts of energy, quantities that could be defined as kilowatt hours or joules. But in reality, these things aren't equal. It's because you can't use them for the same potential. They have different values in their functions. And so the problem with energy systems today is that, in fact, they're designed with the wrong exchange rate. And the way that we can approach this is by thinking of thermodynamics. And Exergy, in fact, that is a combination of first law and second law of thermodynamics, which represents the energy and entropy parts. But really, for architects, are we really going to talk about thermodynamics? Well, hopefully, by engaging in a conversation about how the concept of low exergy, or as what we define in Switzerland as LowEx, will provide the ability to create a framework, not necessarily a thermodynamic expertise, that will engage you in a little bit more of a dialogue with the engineer about how systems move energy throughout the building. But I will jump through very quickly the equations, which show that there's two parts of energy and entropy balance. And the one thing I'd like you to understand is that Exergy represents a value of energy that tells us how an amount of energy can be utilized. And I'd like to use this analogy to give everybody to represent this. So here's an amount of energy, right? And so some portion of it can be used to do useful things. That's what Exergy is. And some portion of it cannot. And that may seem a little bit abstract, but let's think about a waterfall for a minute. If we want to get energy out of a waterfall, right? How would I get all the energy from the waterfall? Just like if I hold my bottle up in the air and make a waterfall sort of contain the bottle. If I want to get all the potential energy out of this water, right? If I let it keep going, I have to stop, right? So if I stop it, I get all the potential energy from falling into the air, right? Except for the frictional loss in energy. But in reality, can I do that on the waterfall? What happens if I stop all the way out? The waterfall doesn't exist anymore, right? So if I put a cup, I can't just leave a cup there forever. It's going to overflow. We have a problem. So in reality, to capture water, energy from the waterfall, we have to let some of it go by. We have to. It's because we exist in a place where time is moving forward, and there's no way the water will spontaneously jump back to the top of the waterfall for us and keep going in circles. This is the same reason we can't have perpetual motion machines. It's because some amount of energy has to be allowed to flow by for a flow to exist. And the exact same thing is true for heat. In order for heat to flow from one place to another, there always has to be a hot and a cold place, and some of the heat has to continue flowing by. And this exact quantification of the amount that you could actually do something useful with is very important in defining the usefulness or the value or the performance of a system that is in operation. So the main thing you have to remember, you don't remember the equations, but if we look at them, just remember that the temperature difference in a system, that little number there, T minus the temperature of the environment. The important thing about Exergy is that it takes into account what that temperature difference is. So if we talk about energy systems, the energy system would just be about how much water is going over the waterfall. What Exergy does is it also tells us how high the waterfall is. So it tells us what the potential might be, how much we could actually utilize. So all the equations are just a detailed way of saying temperature matters. Temperature is important in buildings. And if we would look at coffee, it works for coffee too. If we would look at espresso, it actually has more high quality energy. Even though it may have less energy, it has more high quality energy in the form of Exergy than our lukewarm McDonald's coffee, which is very fun to make fun of in Europe, but back in the US, I'm struggling with this one. And there's also the cool Exergy. The nice thing about defining things in terms of potentials is directionality kind of goes away. You have the environment of a building is a fixed quantity. And now as the environmental temperature around my building changes, that just tells me the amount of potential that the air has in the building, right? And that's really all I have to deliver. This amount, if it's 10 degrees outside and the building wants to be 20 degrees, I just need to put in a system that makes that differential exist, right? So in reality, it's about matching up temperatures. And in terms of cold systems, the same thing. This is a nice example because if you think about people that like root beer floats, some people like them after the ice cream melts, right? But in reality, if you look at this system, the thing you desire is the melted ice cream that's now in equilibrium, let's say at 10 degrees, and you have half and half ice cream root beer before. In reality, because this ice cream was much colder, it actually has potential to so this is the problem often with buildings. We often subcool, or we do have to subcool the air in the building to remove humidity. And so there's all this added value that gets put into the air streams in the building, and that makes it very challenging in terms of just with energy balance alone to define some of those potentials and the places where we can improve them. The argument that we generally made in the heating case in Switzerland was that the combustion is the main problem, and that heat pumps, rather than fire, are the best solution for moving heat into a building. So the key thing here is that we move heat instead of generating heat by burning things. And the most important quantity then is the coefficient of performance that tells us how much heat we can move with every unit of electricity. And in fact, when we move heat from the ground, right, the temperatures get closer together. So the idea is to find places where we can get higher temperatures at sources, and it makes it easier. It's just like how hard would it be to carry a bucket of water to the top of the waterfall. This is what a heat pump's doing. It's a system running in reverse to deliver a potential, and that potential is in fact this temperature differences in the building. And again, it's the temperature differences that are the key component. I want to get to the project, so I'm not going to dwell on the system level. So again, the performance of the system is directly dependent on these temperature differences. So standard heat pumps we buy now operate in this sort of flat region. So we usually have COPs, which means moving about 4 units of heat with every 1 unit of electricity. Now that sounds good, right? 4 units of heat for every 1 unit of electricity. But the problem is that a power plant is also burning fossil fuels with an efficiency of about 30% somewhere upstream. So this is why generally natural gas combustion systems are thought of as being, on par with the heat pump. But what we're looking at doing is designing systems and buildings that leverage temperatures that are much closer to each other. And so that way its performance moves up into the range of, say, 10. And we can move 10 units of heat for every unit of electricity. That changes the game completely. And that means that there's an ability, if 10 units of heat or cool, both works in both directions, can be added or subtracted from a building with just 1 unit of electricity. What does that mean for the size of that roof, the building that we saw at the beginning, right? Now we reduce the amount of electricity it takes to run that building independent of any of the other facade or structural components of the building. So traditionally when we design a building, we start with this quantity of energy that needs to be added, right? This is the facade equation. The heat equals the transmission losses and the infiltration losses. And so by increasing the performance of the facade, we can reduce that quantity. And that's an important first step. But the thing we often miss is looking outside of the box and understanding that the source of that energy has a certain potential. And so by looking at systems such as geothermal wells or activated panels in buildings and radiant floors, those systems help move temperatures closer together and in fact make the well where we get the energy from shallower. So this is a completely different paradigm for how you increase the performance of the building. It's not about making the walls thicker, it's about thinking about systems, ones that are quite relevant to how you design the inside of the building, perform better. So a LowEx building then is one that isn't necessarily a combustion building, but it's also not a passive house. So the idea isn't just to have the thickest facade possible. It's about having the right amount of insulation, not the maximum amount of insulation. So what about the Tropics? So a new paradigm needs to be developed that has appropriate temperatures that uncovers these higher potentials. So I want to take you through 4 projects. The Bubble Zero that we worked on in Singapore, and then about the complex delicate design. And then 2 projects that sort of were subsequent to that about the non-integration of components in design, and then about how actual integration of components can work. And then finally, we'll wrap up with what you've seen on the walls. Mysteriously appear this Thermoheliodon thing. It's in the back of this poster that I've seen my name on around. So first, the Bubble Zero project. I'm going to do the flash slideshow of how you build a laboratory in Switzerland, send it to Singapore, and construct it, and then operate it without dying of heat exhaustion. So in Switzerland, you get some containers, flip them over, throw some insulation in them because you don't want to melt and heat. And then we add some thermal mass by pouring concrete in them. Add some ducting to the floor, put in some additional welding so that the floor doesn't fall through. Flip the things over, put a raised floor on one side, so one side has a concrete roof, one side has a concrete floor, to test thermal mass systems. Then we put in some panels that are increase the surface area of the heating system, which is very important for these low temperature, matching the temperatures of the systems. And then we install some sort of walls so we can hide behind the doors, fill it up with insulation, piping, manifolds, of course all the lights that we need there, and then ship them off to Singapore on this very boat. And then in 4 months, you set these containers down, pray that nothing's broken inside, open them up, glue all that insulation to the outside, wrap the thing in a giant inflatable shell, and this is the name, where the name, bubble part of the name comes from, and then race a storm to get it onto without being struck by lightning, and blow the thing up. And you end up with this little shell that then keeps us from melting in the heat. Because a container sitting in the sun in Singapore is not a place you generally want to be. And what this then allowed us to do is by having this sort of integrated shade, we also had a bunch of tubing underneath here on all of the sides and underneath the concrete inside so that we could simulate that the walls of this sort of small space might be the same temperature as an adjacent space. You can imagine these two containers next to each other. We could make this wall, and this wall all feel like they have like air conditioned space next to them. And so we cut out those walls inside and installed some glass and all the pipings I mentioned. You can see some of that over here. And then demonstrated it to the locals. This was our first home. But in Singapore, there is a little bit of bureaucracy once in a while. And we did have to get evicted. So here's a nice picture of moving to our new location. And there's where it sits now, next to the career lab. And here we're investigating, and you can see with the new, this is about studying the solar angle. So this is very important. In Singapore, we have the challenge that we're at 1 degree north. So what does that mean for passive solar design? That means south or north doesn't matter anymore. All that really matters is east and west. And so we were studying ways, what kind of angles you would use, and different solar shading models, and how you use special kind of glass in this case that is highly reflective in the infrared and ultraviolet to try and minimize the amount of solar heat gain that we have in the space. You can see that better here. These guys are activated at different angles to reduce the amount of heating that comes in during when there's direct sunlight. So you can see on the inside, the full installation, we have these radiant panels that provide cooling at a very high temperature, so very close to the room air temperature, and the heat pump system that delivers it. But in the end, really, the goal was for the Bubble Zero was this concept that I came up with there related to this idea of complexity. So what is elegant complexity? And so that's the idea of this is where this word pleasingly ingenious comes from. So a little side note then, how many of you ever played with Google Ngrams? So this, I did a quick example for you. This is this tool in Google, right? Google makes all kinds of crazy tools, but this one plots the percentage of word usage in books over the last 200 years. You probably like this. So in this case, I did a quick one today just to give you an example. So this shows that Hawkeye is slightly more important than Buckeye 6. Very important. It took me a while to find that to work that way. But luckily for you, architecture is still more important than football. But what I discovered that actually I think is more relevant to the Bubble project is that in fact it's very interesting. This is the exact same scale. So the exact same usage of the word elegance now mirrors exactly the rise of the use of the word complexity. And this was the challenge because the problem with the Bubble Zero as a laboratory, right? There's a lot of complexity in setting up those systems. Something that is very difficult to translate into an architectural design, right? So we ended up, it was fun creating the bubble, there's a lot of form finding, but then we get down to the nitty-gritty part of actually connecting all those pipes and getting things to run and controls and sensors. That becomes complex. But the question then was, is there elegant complexity? So what I discovered, and that's why I use this word a lot in terms of the bubble, is that if you take this, the definition, just about the simple and neatness part. I really like this part, the pleasingly ingenious part. So I think that's something that, as an engineer, I think that's a place where you as architects or me as an engineer can find a sort of common ground. Like things that are pleasingly ingenious. Engineers kind of like to do the not simple, not elegant part by making it complex, but I think somewhere in the middle there's something interesting there. And so the part of the bubble that was sort of pleasingly ingenious with all these like great sensors that I could play with that monitor temperature and humidity and CO2 sensors, and we had all these panels inside here and these little ports where they were open or closed based on the amount of CO2. So air was brought into the bubble through these little boxes that you see on the floor here. And the really nice control move, so this is a CFD simulation of how the plume rises in displacement ventilation. So displacement ventilation is when air is brought up from the floor. And what we did is have the CO2 steered exhaust so that if we all stood in one corner of the bubble zero, then only the port above us would open, and so all the fresh air would move over toward us, and we would get a larger fraction of clean fresh air, just based on the simple control of the exhaust vent, right? So one other example of the sort of elegance of the operation of the system that plays out for any radiant system, such as radiant floors or radiant ceiling panel, is if you envision our friend here sitting in the bubble, right, and this panel is all about 18 C or 65 Fahrenheit. If there's an added load, right, and that room air temperature increases, right, a normal building system would have a thermostat and say, whoa, it's too warm. And we turn on a fan and blow a bunch more cold air. And usually the cold air generated in those systems is in very cold coil temperatures, right? And so this is why when you sit by the vent and a bunch of the people on the other side of the room, you're always kind of cold. So these systems have a feedback control. But now imagine the physics of this system when the air temperature rises. What has happened to the temperature from 18 to here? This was the normal operation with 3-degree temperature difference. And now I've increased the air temperature by 3 degrees, so it's in essence double temperature difference. And what did we say about temperature difference? It drives the heat transfer. So the physics alone, by having a temperature close to the room air, now when the air temperature increases, just with the physics, I have 2 times the temperature equals 2 times the heat. And the system responds without any control operator, just based on physics alone. And on top of that, the radiant heat exchange, you're not just an exchange with the environment in terms of convection, right? The air around you is usually is your proxy for comfort if the air temperature is right. But in fact, if I shifted all the surfaces around you in this room by 1 degree cooler, you would think that the air temperature had dropped by 1.4 degrees, just because of the physical phenomenon of your exchange of radiant energy with the surfaces around you, right? So there's different ways that heat transfer. And your comfort isn't necessarily about temperature. Your comfort is really about the metabolic rate of your body wanting to be at the most comfortable equilibrium with its environment. And the environment interaction takes place through different kinds of heat transfer, including radiation, right? So this plays out across both cooling and heating scenarios. So if you have a radiant floor, you have the same phenomenon. These temperatures that are close to the room air, meaning A, more comfortable, and B, more efficient. So the next two examples I want to run through really quick in terms of Singapore is how this then plays out on a larger scale in terms of building system design and space for building systems in the building. So as I alluded to earlier, if we talk about putting the right amount of insulation and how space gets utilized in buildings and where we put value, if I start adding insulation to a building, that first half centimeter of insulation is very important, but if I do a passive house, this would be the amount of insulation I would need in order to achieve a passive house standard system. But in fact, that last 10 centimeters, or that last 3 inches of insulation that I added, did exactly the same good as the first half centimeter, so 20 times more. This amount of insulation, 20 times more than this amount, gave you the exact same return on performance, right? So we have to understand that there's a diminishing effect of insulation. And it's important to understand that passive design is important, so you still need a little bit of insulation. It does a huge amount of good. But there are other components that we can consider that can increase the actual performance of the system. And so the first case study, as I alluded to earlier about non-integration, is how to ignore hybrid systems. And we're going to start with this great building in Cantonville 2 factory housing, my home in Singapore. And what we're going to talk about is these things, these beautiful split things. They're lovely. And what do you think happens? How do we do these things here? Right? Interconnected to those wall-mounted cooling devices that blow cold air out. But by blowing cold air out, right, that basically means they're pushing heat somewhere else, and this is where they're pushing all that heat. So how do you think the temperature is around these things? And especially in this one, what do you think is happening with the heat that's being emitted by this air conditioning unit? And in our towers here, they have them also in a stack configuration where you might expect the heat tends to rise. And as any good architect that wants to win a Revo award, as he did, you would hide them, right? So this is sort of where are those split units? Oh, there they are. You just have to look at them angle because it's these smart little louvers that protect your poor eyes from having to see these ugly technologies, which I would agree they are ugly and inefficient, to be honest. But it doesn't consider this effect, right? That all the heat is going to be going, up to your neighbors. And so what we did was install a bunch of sensors in these cavities and measured the temperature along this profile. And the most fascinating thing we found was that not only was there a significant stack effect where these systems had 10 degree higher temperatures at the top of the building, but on top of that, the louver move actually increased the air temperature of the split units on this side of the building by another 10 degrees. So all the heat is thrown off to the side and rises up the building. So whoever's living on the right apartment over here at the top of the building, they're not going to be too happy with their energy bills. Luckily, I got an apartment on this side of the block. So in the end, it would result in 32% more electricity demand that otherwise is completely ignored. Nobody would even know about this actually unless neighbors talked about their energy bill. That's probably not a common conversation. So a better solution would be to move energy around hydronically, right? Water is 1,000 times more dense and has 4 times the heat capacity of air. So why don't we use that physical characteristic and try and think of ways that we can pipe heat around the more effective means of getting rid of energy. And considering how expensive a square meter of shop space is in Singapore, the fact that they just use the back lanes as sort of dumping grounds is something we're very interested in. And we have a project there on the urban scale, reactivating these spaces by redesigning how energy systems in terms of the waste heat as well as the waste garbage is removed from the system. So there are ways you could model these systems in an urban environment, and obviously there's better fixes than this. It involves taking a simple cooling tower system using evaporative cooling. You can get a much better temperature to remove heat from the buildings. And so in that way you're engaged sort of in a technological solution that then provides back to the urban design more accessibility and freedom again. So the argument then for the technology, which is more high performance, it's really hard to argue for performance paybacks, but when you start talking about the value of retail space in Singapore, then you have a very powerful argument. Now another case, similar argument about added design components is added freedom in design is this 342 project that we're working on. And so it evolved from the fact that our laboratory had this 2-meter high space in the building. This is our office, not the bubble lab. But you can see the drop ceiling there, and here it's removed. And all this space was just put in by default, right? By the architect. So about a third of the space is just put in for systems without any consideration of how that could be used. And I did try to put my PhD students up there on desks, but they just wouldn't let me do it. And we did an analysis for a more generic case, for power. This is one Raffles key of classic power in Singapore. And if we would redo the building using these systems that take out the ducting and integrate it into the floor slab and reduce the height of the building, we could have 40% less cooling energy, because don't forget we're also getting rid of all the facade, all this glass that's up here. Again, my problem with glass. In this case, it's not that I don't like the glass, it's just that I don't like the irrational consumption of space by the building systems that in fact I'm supposedly responsible for. And so we talk about this in this generic case. You can see there's a huge amount of saving in terms of energy, office space, facade material, structural concrete, and installation space, and with added comfort. And so in the end, really, again, this is another example where there's the potential to design something that adds more value, not necessarily just in terms of performance. And this is a building that we're working on right now. It turns out being evicted was good with the Bubble Zero because we met these guys that were building a new building on their campus. This is where we have the bubble sitting now, and so they invited us to design for this building using that 342 concept. So it's going to go in on this area here, and we're in the middle of building that right now. So now, kind of running out of time, but I want to get back to Princeton, as was alluded to, and what I did this summer, which was building upon this event that I had, looking back at the old days. We're working on building technology at Princeton in the 1950s, because in fact, when I went from Singapore to Princeton, most of my colleagues in history and theory working at Exergy really questioned the technology guy going to Princeton. But I was game, and I went and actually found out to my delight that there were interesting things going on, which started the Thermoheliodon, which is something they had built there, and then started my adventure, which led to this summer developing this thing called the Thermo, which I named in honor of these guys, the Thermoheliodon. So in fact, Princeton has a long history of technology. This is the architectural lab being built in 1950. And they invited these two faculty members, Hungarian twins, Alan and Victor, to look at energy systems. And here's the thing that they built with Thermoheliodon, which studied the solar angle and the effects of climate on the performance of buildings. And subsequent to their work, there was also work in the engineering department on passive buildings and energy consumption. And this was all at this architectural laboratory where also many other prominent figures came through the time working on different aspects in building performance. And right now, our current plan is we're going to be renovating this space because we have a new tenant. As of 2013, Professor Axel Killian, who does computational design, brought in our friend the robot here. And then subsequent to that, we had this event that was mentioned where we looked at the historical research that had happened in the area and talked about how we're going to move forward. So I subsequently hired 10 crazy students over the summer who, as an engineer, I had to give them a name that had a great acronym. So we were the Chaos Lab for the summer, cooling and heating for architecturally optimized systems. Very proud of that one. Just so you know, if you ever have to apply for government grants, you have to be good at acronyms. So our team then consisted of 2 architects, an architectural engineer, a mechanical engineer, civil engineer, chemical engineer, and 3 high school students, and was done in collaboration with the electrical engineering department, civil engineering department, and the chemical engineering department. And what we were looking at was a way to combine radiant exchanges, look at how we could take a system of a pavilion and do indirect evaporative cooling using a new reflective radiant system. So that a couple of the different concepts that were evaluated was basically how you do structural form with pipes embedded in it, how you could potentially develop a new tile material that lets water flow through it and evaporate through it. So basically like vortex for a building, water from the outside and allows evaporative cooling to happen through structural material. And then finally, how geometrically we could then reflect radiation from this single source out to an occupant. So evaporative cooling, as you all show very well here, and you all love the psychometric chart, I'm sure, is the way that you get to colder temperatures simply by evaporating water, right? And this is very important. So like sweating in a swamp fluid, these are the classic sort of evaporative cooling systems. And what we used was a cooling tower, basically, to get to the colder temperatures simply by letting the water flow through the air in little droplets and a fan blowing the flowing air across those droplets, causing them to cool down evaporatively. So there's no compressor, no air conditioning unit. We get cooling for 10 times less. The fan power is 10 times less than, one order of magnitude less than the chiller would otherwise use in the system. The initial concept was something sketched out on my desk like this, where we had some structural panels here. We had an idea that had this parabolic form for the reflection part, and we're going to have this evaporative cooling channel. And then the students came, and before I could even show them this idea that I had, they built an umbrella. Which I was pretty impressed. So this was the first stab at the reflection part and pumping water sort of into a system. And we had this thermal camera, and you can see the idea was to try and reflect that cooling off the surfaces. And you can see it sort of happening here but the problem, the dimensions of the pipe weren't quite right to the scale of the reflective system, right? So after a two-week exploration, we started thinking more about the geometry, and what I realized was, in fact, the problem with the radiation of a person, right, is a person has radiation going in every direction, diffusely. So if anybody's ever seen a parabolic trough solar collector right there in the desert in Nevada, where the sun hits the trough and it concentrates light on the pipe, heats it up. The exact same reason why those things don't work when it's cloudy is the same reason why we can't use the parabolic form to do cooling on a person in space, right? Because if we look at that idea of the parabola, all those parallel beams coming in that would hit the pipe in the middle, in this scenario. Unfortunately, a person standing here does not emit all parallel rays, and you emit everywhere. And so we had to come up with a different form. The idea then was to build cones so that when you emitted in different directions, you could have better concentration. So this was a study on how the different geometries would create different focal points. And in the end, the simplest way to do it was to build cones that we could stack together, so that when you stood here, your radiation would hit this stick in the middle. So the next thing that we did was design basically a simple axial pipe, so water goes down the outside up through the middle, so we can cool down that little stick. And so from the origins of the Thermoheliodon, we built the whole thing as a sun path. So we used this sun path of the Thermoheliodon arch to create our form, which then ended up looking like this. And then we had to pack all of these pieces, there's 155 of them, into 24-foot long pieces of foam that look like this. So I'm just going to run through this right at the end. You guys can jump in and ask questions, or I'll just start describing the sort of process. So what we then tried to do was figure out a way to simply fabricate this with the least amount of material wastage, first of all, for environmental reasons. Styrofoam, as I learned as a kid, is like the worst thing for the environment. And so we had found a way, first of all, we did find a way to recycle it, thankfully. But we also had to strategically pack it into these forms, so we made these triangles that would alternate and then create the raw pieces that then we could attach to the robot. So in this case, we had this wire cutter and a little jig, and then we figured out we had about plus or minus 2 centimeters to cut through these lines and pack all the pieces into the blocks of foam. So this is what it kind of looked like the process. And then the most important part was my students didn't want to make t-shirts, they wanted to make coveralls. But you get a really scary system for picking up the foam, of course. And then each one of these blocks, they had different versions. You kind of lock them in place, and then the robot would pick them up. And as you shortly see, dragging them then over to the tool, which was a hot wire cutter, basically mounted in space, and they would create all the forms that we needed. And the important part was we really needed the geometry of the cone to be assemblable. And we had the architectural students' main design challenge was how do we create this so that we can also put those bulbs in as we build it. So each cone was actually fabricated from 3 different pieces that came together. And so you can see some of the finished pieces in the background. But you have to basically cut each one of these little curves in midair, and then figure out a way to stack them together so that you can insert the pipes into the system. And so there's a lot of time, testing and calibrating these tools so that we knew exactly where in space these components would be, and then there were many long hours spent making sure, because with the digital fabrication, sort of this prototyping mode, it's not something you can just let the robot run on its own. In fact, robots are very dangerous when you let them run on their own. You always have to stay in control of the process. And a little stabby thing in the back that hits at the very end was our alignment marks. So that was the way for the construction process. And so you can see it starting to be fabricated. The other challenge was I didn't want to have to ask facilities for any big pieces of equipment to build it, but I needed to put pipes around the top. So instead of building it on its normal position, we built it on its back so that I could just use a ladder to put all the pipes in. So here you can see it slowly being assembled, and you can also see us slowly discovering that whenever you do the wire cut, the wire starts hot and gets colder, which means actually you get this little bit of hysteresis in the process. So even though we have this beautiful model and all the pieces are cut exactly to the right geometry according to the robot didn't know about the temperature of the wire. And so in the end, the lesson is in terms of planning, there's always going to be a component, even if you have this perfect digital fabrication, in reality, physics isn't always digital. And so here you can see that this is just before the lift of the floor. So in order to set it back down, we brought the floor up to meet it so that we could finish it, put in the remaining pieces. So we threw a rope up in a tree, wrapped it around, and pulled the floor up the rest of the way so that we could build the rest of the pieces in place. So really a lot of, this is kind of, if you're ever working on a project, you'll find very quickly that in terms of skill sets, engineers and architects play very well together when you're actually in the middle of figuring out a project. Because the architects are the ones that always had a spatial solution for how to get the systems to fit together, and then the engineers would always figure out how to make the process work, or how to build the form that would actually make things stand up very quickly. And so then you can see the floors sort of sitting there. In their spare time, of course, all students these days apparently build drones. So with all the raw material that was laying around, several drones were mysteriously constructed, and just attached cameras to them to fly around. And as a result, actually, of that side project, we're now going to attach one of the thermal cameras to the drone and fly around the university to show them where all the buildings are efficient. So this is the most exciting moment. Hey, okay, because I didn't really know how it worked. So it didn't fall apart. And then, I mean, once that was done, all the pipe was mounted and everything, this was mostly built in about a month. And then it turns out the last 2 months, there's been much more of a challenge on the digital side, setting up all these different components in terms of how we actually measure what the phenomena that are inside. So we've tried a bunch of different systems for infrared. This is, instead of just using, we also have a black hole thermometer that measures the radiant temperature, but one of the students built a little Arduino IR camera that spins around and records the radiant temperature, but then you can see there on the left of the image of how the temperatures change in the bolts. So you don't just see the bolt temperature then, you see the temperature reflected out of the cones. And so this way we can calculate what the actual surface area the virtual surface area that you see in the system when you're sitting there is much larger than the actual surface area of the radiant black bolts, or the water, the cool water flowing through the system. So that's the Thermoheliodon. And right now the status is we're running both tests on what the physical parameters are, so we have those sensors inside, but we also have the thermal camera to measure the physical properties. When you sit in the center of the dome, in the area in the middle, you have a much larger radiant temperature suppression. But most importantly, we also have physical evaluation from old farmers from Iowa that sit in there and tell us what it's cold there. And so that's the status. Right now, the overall we're getting about, even on a relatively humid day, we get about 10-degree cooler temperature into the bulb, which results in about a 5-degree shift in the mean radiant temperature. So all the people that sat inside could perceive a colder temperature than their actual temperature, but unfortunately the time it took to set everything up, the weather all of a sudden got cold again. So now we're reversing everything and setting it up for heating and trying to run some tests. In that case, although there's other challenges that happen in that in terms of how you heat the outside. It's a little bit colder than it is warm. So with that, I'm sorry I'm running a little long, and I very much appreciate the opportunity to come show you something.